Pizza.
All right. Thank you, Abhi. An era of characterizing exoplanets, not just detecting them, but learning things about them. These two plots are just quick things summarizing the kinds of things that people do, specifically people around here. This is the transmission spectrum of the super-Earth GJ1214b, work by Zach Berta. This is plotting planetary mass versus radius and seeing where exoplanets land, so getting some kind of insight into their compositional structure. This is thing that these are really big industries right now. As a person with a background in radio astronomy, I'm trained to ask a question that comes up so often, there's even an animated GIF for it. What about the magnetic fields of exoplanets? Can we learn about them, too? And it would be really nice to. So one thing is people talk about a lot is habitability. And obviously from our own solar system, we know that a planet's magnetic field plays a big role in its response to its space weather environment. Coronal mass ejections, direct interactions with the stellar wind, things like that. So this is an animation from Ofer Cohen just showing a close-in planet. And what's happening here is this planet is so close that there's an interaction between its own magnetosphere and the magnetic field of its host star, leading to reconnection events, driving things like this big outflow. One thing that I think is particularly cool is because the magnetic field is being generated by the planetary dynamo, detecting it really gives us insight into the interior structure of the planet. So this is just a pretty much randomly chosen animation of mantle convection in a rocky planet. And you can imagine there's a relationship between convection in the core itself, which drives the dynamo, and in the mantle. So learning something about planet's magnetic field could actually tell you something about whether, say, it has active plate tectonics, like the Earth, or is inert, like Mars. So, how do we want to learn about the magnetic fields of exoplanets? There's a few different methods that people are working on. I want to argue that radio observations are going to be very important for this. First of all, it's just a regime where the planet-star flux ratio can actually be larger than 1. So this is a plot of the radio spectra of various solar system objects. So here we have the sun when it's not active, decreasing down to around 10 megahertz here. And here's Jupiter. And Jupiter can be brighter than the sun. Even Earth can be brighter than the sun at kilometric, very long wavelengths. And this is because the radio emission that you're getting from things like planets, this is auroral radio emission, which is coming from a coherent maser process where you get very high brightnesses with relatively low energy input. So despite the fact that you have a lot less, the energy scale of the planet is a lot smaller, you can still get very bright emission. Another nice thing is that this emission carries a lot of physical information. So this plot here, this is a radio time frequency diagram. This isn't actual data, but it's derived from data. So we have the frequency over here going up and time progressing right to left. And so this auroral emission has a few characteristics that make it very useful. It's very beamed, so you end up getting a pulsar-like effect, where you have periodic radio bursts at the rotation period of the planet. Also, the characteristic frequency of the radio emission turns out to be the cyclotron frequency of the magnetic field. So if you detect radio emission at a certain radio frequency, you can read off the magnetic field strength right away. And then this plot here is showing, in this particular observation, there's 3 bursts that you see every rotation, which help you infer the fact that there are 3 magnetic loops where there's probably more magnetic loops, but these are the 3 where there's some kind of current system that's driving the auroral phenomenon. So basically, your temporal resolution can become spatial resolution, and you can learn about the magnetic field structure of the planet itself. Now, we can't actually detect exoplanetary magnetic fields through radio, or as far as I know, any other direct means yet. But we're working on it, and something that's really coming clear right now, which is just coming into focus, is that it turns out, kind of extraordinarily, that brown dwarfs are they really seem to be scaled up versions of the kind of auroral magneto-ionospheric current systems that we expect, or that we do see in solar system planets, and that we expect to see in exosolar planets. So I just like these plots. So this is the discovery of radio bursts from Jupiter back in 1955. This is Ito's discovery of radio bursts from the first brown dwarf in 2001. I kind of like the visual analogy there. And I can't show some other things because they're not published yet, but there's a few lines of observational evidence that are really indicating that there's a scaling over a factor of, say, 100 in mass. And one nice thing about the brown dwarfs is that the luminosities are much larger, And also the magnetic fields turn out to be much stronger, which brings the emission from very long wavelengths, sort of 10 megahertz, where you're even worrying about the ionospheric cutoff, up to the gigahertz regime, where we can use very powerful observatories such as the VLA. So while we're waiting for the SKA low to get built, we can still make a lot of progress and work towards understanding how we get physics from these kinds of observations. That being said, while we can still observe brown dwarfs that are relatively warm and they seem to have analogous processes, we are interested in seeing how cool we can go. What the coolest brown dwarf we can detect is, how close we can get to the exoplanetary regime. The current gold standard is a T6.5 dwarf called 2-mass 1047 plus 21. So it was first detected in a survey with Arecibo with isolated radio bursts spread out over around a dozen observations over a course of 13 months. So these are more time-frequency diagrams, and these plots integrate over frequency, showing you these bursts that are evolving on kind of 100-second time scales. So quick radio bursts, but not fast radio bursts. So Arecibo has some limitations. You can't detect very faint quiescent emission because it's a single dish, and because it can't point, you can only track things for about 3 hours at a time. So a couple years ago, we did a pilot study with the VLA. We didn't see any of these bursts, but we did confirm radio emission at a quiescent level around 20 microjanskis, which is radio astronomer for very faint. And that motivated a follow-up study where we decided we'd really see how much we could learn by staring at it with a VLA. So we did that, and this is what we found. This is basically the radio light curve shown in a few ways. And the first order result is we see radio bursts that seem to be spaced around periodically. And I want to emphasize that something like this or that, they don't look like much in this rendition, but this is around a 7 sigma event, and this is kind of a 3 sigma event. And I'll carry on with this dying pointer. So this top panel here is showing the emission as a function of Stokes type. So the red upward lines are Stokes total intensity, and the blue downward are Stokes circular polarization, Stokes V. So this is showing you that these radio bursts are basically 100% left circular polarized, which is what you expect given this coherent emission mechanism. Bottom panel, we're breaking it down by we have 2 frequency windows with a VLA. And so there's 5 and 7 gigahertz. And basically, the key thing here is, so obviously the pulse amplitude and structure varies with time, and so does the frequency structure, if you break it down that way. That can tell you something about sort of where the emitting region is propagating as it moves. So that's averaging over the 2 spectral windows, so a mean frequency of 6 gigahertz. And so one other thing you can see is, these peaks are pretty comparable, so it's a fairly flat spectrum, which again is a characteristic that you get with the radio bursts. So something like this, where the pulse shape varies from one event to the next, it's a little bit hard, or some kinds of ways of measuring a periodicity, it's not going to be a super precise value. But with phase dispersion minimization, we get a value of 1.77 hours with uncertainty of about 0.03 hours. Oh yes, and I should say that, so we have another batch of data that I'm not showing here, where you detect a radio pulse at 10 gigahertz, which again, you map that to the cyclotron frequency that tells you that the magnetic field strength of this 900 Kelvin object reaches around 3 kilogauss. So we're maybe a factor of 8 warmer than Jupiter. We don't know the mass because we don't know the age, but the magnetic field strength is around 200 times stronger. Because we have a rotation period, we can see how the magnetic field scales with rotation. This is something that is very relevant in understanding how the actual dynamo process that generates the field works. So what we're showing here is radio spectral luminosity as a function of rotation as parameterized by V sin I. That's the measurement that we usually have. A lot of upper limits, breaking it down, green, red, blue for M, L, and T dwarfs. Apologies if you're red-green colorblind, but it doesn't really matter a whole lot anyway because there isn't much of a strong correlation. These vertical lines are the flares versus the quiescent emission. And the lack of this correlation is interesting in and of itself because, say, for active stars, there's a very strong correlation between, say, rotation and X-ray luminosity, something that's very well trodden. In the regime where you have a fully convective dynamo, that seems like it may not hold as well. And there's a lot of debate, mainly in the geophysics community, about how the dynamo, how it scales with, say, rotation. And the other thing I want to point out is this is only the 6th rotation period measured for a late, mid or late T-dwarf, and the other ones come from from optical infrared monitoring, where you're assuming that you're watching the cloud, or you're watching inhomogeneities due to the clouds, and the clouds probably evolve on similar timescales, so you worry a lot about what you're measuring when you're seeing kind of stochastic variability with a certain timescale. Radio observations don't have that limitation. One other thing I quickly want to mention, tomorrow is CFA Hack Day, so basic idea is we're having a space in the Woolbach library. Ideally, just sit down and spend a day focusing on a problem. Do something that you wouldn't otherwise get to do, sitting in a room with people who know a lot about technology if you want to work on something technology related. You can just build something cool, fix something that's been bothering you. Obviously, not everyone can afford to spend all day there, so there's a few key times in the morning. We'll get together, have some bagels and coffee from the fancy new bagel place. People discuss their projects, assemble in teams. We'll have pizza and some brief talks at lunchtime in a format hopefully similar to what we're doing right now. And at the end of the day, people who've been working on things can summarize what they've been doing, show off what they've done, we can celebrate. If you've been hearing about Git and Python and wondering whether they're right for you, don't talk to your doctor, talk to us. We'll have office hours. You can swing by, ask questions if you're kind of curious about these tools. And I just want to quickly show, so what I'm planning on working on is I've re-implemented all of tech in JavaScript to make it render anything on archive into something that's a lot more easily readable than a PDF, which is designed for printing on little rectangular pages. Talk to me tomorrow if you want to understand why I think this is reasonable. Here's a summary of my points, and I'd like to thank you for your attention. Exactly, and a lot of people at the CFA are working on this. I don't know if Ofer is around here somewhere. But yeah, both observationally and theoretically, there's a lot of work happening here on just that topic. One thing that comes up is if a hot Jupiter is tidally locked, it's relatively rotating at a few days, which is relatively slow. And there's debate about whether that will stifle the dynamo. Again, it goes back to whether the relationship between rotation and how the dynamo gets driven. So it may be that something in a hot Jupiter situation, its magnetosphere is relatively weak, but we're really just beginning to understand these kinds of questions. Yeah, thank you.